So there's a standard way of describing measurements in quantum mechanics. A measurement operator is a Hermitian matrix. M equals summation lambda I v sub I. V sub I the measurement operator gives us lambda sub I and projects the state onto the eigenspace corresponding to lambda sub I. So I want to do this. I want to explain this for sigma x, sigma y, sigma z. Sigma x equals 1, 1, 0, 0. The eigenvectors are plus with eigenvalue 1 and minus with eigenvalue minus 1. And 1/2 sigma x is, I'm going to say this is a measurement operator corresponding to spin along x-axis. So let's draw the block sphere. Plus is spin 1/2 along the x-axis, and minus is spin minus 1/2 along the x-axis. So apply. Okay, so what I want to do is I want to say apply the measurement corresponding to sigma x, get plus 1/2 or minus 1/2. As you get plus 1/2, you know this is the eigenstate, or the eigenstate plus. And if you get minus 1/2, you're in the eigenstate minus. And this is just because sigma x equals summation, or 1/2 sigma x equals summation. Okay, I don't want to. 1/2 plus minus 1/2 minus minus. So this corresponds to the measurement in eigenvectors plus and minus. So if M is a measurement operator, psi is a quantum state, actually what quantum people call this. In quantum mechanics, these are called observables. So let's call them observable. Psi is a quantum state. Then psi m psi is the expectation value of the observable. Expected value of observable. Proof. M is equal to summation lambda sub I v sub I v sub I psi m psi is equal to summation lambda I psi v sub I v sub I psi is equal to sum lambda I v sub I psi squared equals summation lambda I times the probability of observing lambda sub I. So one thing I want to say is that so far we've only talked about something called von Neumann measurement, or projective measurements. And there's a more general class of measurements called probability operator valued measurements, or POVMs. And we are not going to deal with them until later in the course because, well, basically because they're much more confusing than this kind of measurement, and we don't need them until we get to quantum error correction.